Today I'm going to briefly talk about liquid hydrogen propulsion for narrow body and wide body aircraft. So liquid hydrogen was considered in the 1970s a viable alternative to kerosene. The main issue has always been the volumetric density of hydrogen. It's roughly 4 times higher in volume than the equivalent amount of kerosene. Now, the other issue is the weight of the tanks. If they're not properly designed, the tanks add a significant weight penalty that offsets the energy density advantage of hydrogen. So, of course, right off the bat, I didn't really mention that hydrogen has 2.87 times, or about 2.8 times more energy density, which means that you're allotted a reasonable margin to use for constructing the tanks. Interestingly, a narrow-body aircraft, let's say a A320 type of aircraft, such as the aircraft pictured here, the diameter of the fuselage gives you enough storage area to store plenty of liquid hydrogen without compromising too much of your cargo volume and or passenger volume. The tanks can either be in the front and rear of the fuselage, or they could be in the center. They could also be on the top. But anything that adds to an unconventional design is not attractive. We want to keep the design conventional. We want to keep our tubular fuselage. But again, placing the tanks on the top is an option. In addition, placing the tanks in the cargo section, where you have 3 spherical tanks resting here at the bottom, is also an option. The ideal configuration is 1 tank in the middle, and the wing box can be accommodated. So hydrogen, being cryogenic, needs to be kept at low temperature, and in order to do that, we can use vacuum insulated panels. These vacuum insulated panels have a thermal conductivity of about 0.02 watts per meter Kelvin at the low temperature, because you're putting them up against the metal tank, and that low temperature gives you added reduction in thermal conductivity. The density of those panels is about 10 pounds per cubic foot. You can see how it's configured. We have the tank wall. So that would be the structural skin of the aircraft, which could be made of carbon fiber. You want to isolate the carbon fiber from the cryogenic temperature of the tank. Then we can have a metallic aluminum tank. Then our vacuum insulation up against the metal tank wall, and then air passing through here to maintain pressurization differential pressure, because the atmosphere is at, let's say, 3 psi, liquid hydrogen is at 21 psi, and so we want our pressure here to be as high as possible. If we have insufficiently high pressure here, the tank wall is going to want to move outward and cause deflection. Now, the range of the aircraft is significantly enhanced with the use of liquid hydrogen fuel, despite the added weight of the tank itself. Here's a breakdown of the tank weight. You can see drag accounts for 38.6% of the additional weight, because you're adding wetted area, and for every square foot of wetted area, you have a certain amount of friction that you're adding. So the panels are 0.0025 watts per meter Kelvin. Nanopore vacuum insulated panels, J foam S180 foam filler between frames. This is a hypothetical long-range business jet with a liquid hydrogen tank in the rear section. Here is a cutaway of a metallic configuration. So this is your stringer, fuselage skin, vacuum panels. Again, the vacuum panels don't have to be very thick, because your thermal conductivity is so low, especially when it's up against a very low temperature cryogenic tank. The tank is integral with the fuselage structure, so the fuselage barrel is integrated with the tank structure. This maximizes that actually minimizes the additional weight from the tank. Some considerations include the pump. The hydrogen pump needs to be able to provide a sufficient flow rate and be able to tolerate the low temperature. But aside from the tank design, really everything else is pretty standard. The liquid hydrogen can be combusted in a gas turbine with ease. Flashback was an issue encountered when converting industrial gas turbines to hydrogen. So flashback is a consideration that needs to be taken into account when converting a gas turbine jet engine combustor to run on hydrogen. One potential option that arises is pre-cooling the bleed air to cool down the high pressure section of the turbine with liquid hydrogen. That's an option that is potentially feasible, and that was actually studied by Daniel Brewer, who had done extensive research on liquid hydrogen aircraft. So I would go through this article here that I wrote. It's of reasonable interest. So tank parasitic drag penalty is why you don't want a blended wing-body aircraft, because your surface volume ratio is quite poor. You want one large spherical tank, ideally in the center of the fuselage, as pictured here. In summary, liquid hydrogen is an attractive fuel because it offers this tremendous increase in payload. The downsides are a reduction in cargo volume or passenger volume. Another possible downside is unless the cost of hydrogen can be brought down to about the price of jet fuel, it may not be attractive. Safety is really not an issue. It's comparable safety to kerosene. Fuel pumps, the plumbing system is really not significantly different. The gas turbine, aside from flashback, requires minimal modification. The potential to cool bleed air, the integral tank, the tank skin itself adds structural integrity to the aircraft. The tanks can be removed. Ideally, you would have a system where you would remove the nose of the aircraft and you would be able to go inside and disassemble the tank assembly and reassemble it occasionally for maintenance. But yeah, the payload at max range here is 51,000 pounds, equivalent to a wide body at the same range. Again, the increase is around this margin, around a doubling of the either the range or the payload. Of course, you can either fly longer or you can carry more weight. So in closing, liquid hydrogen has a bright future as a fuel for narrow-body and wide-body aircraft. Unfortunately, scaling laws and the surface-to-volume ratio are not or make hydrogen not conducive to scaling down to smaller sizes, such as a Cessna 172. Of course, I should not forget to mention that hydrogen cannot be stored in the wing of the aircraft. It must be stored in large tanks, large diameter tanks. So surface volume ratio determines your boil-off. Boil-off determines the amount of insulation needed. The amount of insulation needed determines the weight of the tank. And the surface to volume ratio also affects the drag, so the amount of drag you're adding per cubic foot of hydrogen you're carrying. You want to minimize that additional wetted area. So when you scale down to the size of a trainer, the weight of the hydrogen containment system, if you include all of the penalties, drag being a major component, reduce the energy density advantage of 2.8 times down to a margin that may not justify the use of liquid hydrogen. So in summary, hydrogen is most attractive for a narrow to wide body aircraft.